Welcome back, and in this part of the series I'm going to be primarily covering the transport layer, which is layer 4 of the OSI model. I'm also going to be touching upon layer 5, which is the session layer of the OSI model, because there is some overlap for certain features and so it's easier to cover them in one lesson. The transport layer runs over the top of the network layer and provides most of the functionality which supports most of the networking which we use day to day on the internet. The session layer runs on top of the transport layer, and many features which you might use are often mixed between these two layers. Now, as I've already mentioned, it's not generally worth the argument of deciding whether things are covered in layer 4 or layer 5, so I generally explain both of these layers as one grouping of functionality. The OSI model is conceptual after all, and many things exist between or across two different layers. Now, we've got a lot to cover, so let's jump in and get started. Before we get started with layer 4, I want to summarise the situation and limitations with layer 3. Now, we have a functional layer 3, which means that we can communicate between two devices, say a source and destination laptop using a source and destination IP address. If both of these use public IP addresses, it doesn't matter where on the internet these devices are. Layer 3 and IP routing will ensure that any packets generated and sent from the source laptop will move across any layer 2 networks between the source and destination. Let's say that using layer 3, the source laptop on the top generates 6 IP packets, and these are all destined for the destination laptop at the bottom right. The important thing to understand about layer 3 in this context is that each packet is a separate and isolated thing, and it's routed independently over the internet. It might be logical to assume that the packets arrive in the same state, so the same timing, the same order and the same quality, but sadly that's not true. In ideal conditions, yes, but generally if you're communicating using only IP, then you're going to have intermittent network conditions, and that can result in a few cases where the arrival condition of packets is different than the condition when they were generated and sent. One of the first things which we might encounter is out of order arrival, in this case where packet 3 arrives before packet 2. Layer 3, specifically IP, provides no method to ensure the ordering of packet arrival. For applications which only used IP, this would mean complex logic would need to be built into the application to ensure packets could be sequenced in the same way, and this is not a trivial task. Because each packet is routed as an independent thing, it's possible packet 2 could have taken a slower, less efficient route, which is why it arrives later. This is a negative of layer 3, which can be fixed at layer 4. Another issue with layer 3 is that packets can just go missing. This can be due to network outages or network conditions which cause temporary routing loops. Remember, when I talked about packet structure, I talked about the TTL field, which limited the number of hops a packet could go through. Well, if the number of hops exceeds this, then it will be discarded. With IP, there's no reliable method of ensuring packet delivery, and so it's a relatively regular occurrence that packets go missing. Now, network conditions can also cause delay in delivery, and for any latency-sensitive applications, this can cause significant issues. The key thing to keep in mind about layer 3, every packet is different. It's single, it's isolated. It's a different unit of data which is being routed across a layer 3 network using layer 2 networks as transit. What happens to one packet might not happen or might happen in a different way to another packet. Another limitation with layer 3, and this one is probably the one which has the most obvious effect, is that if you think back to the structure of IP packets, they have a source and destination field. They don't have anything beyond that to distinguish channels of communication. Packets from a source IP to a destination IP, they're all the same. You couldn't have two applications running on the source IP communicating with two applications running on the destination IP because there's no method of distinguishing distinguishing between the applications. Any packets sent by one application would look to be the same as one sent by another. Think about what you're doing on your device right now. You might be watching a video. Do you have a web browser open doing something else? Do you have an SSH connection or email or any other application which uses the internet? This means multiple applications. An IP on its own offers no way to separate the packets for individual applications. This is something which is remedied at Layer 4. Lastly, IP has no flow control. If a source device is transmitting packets faster than a destination device can receive them, then it can saturate the destination connection and cause loss of data, packets which will be dropped. Now, with only Layer 3, we wouldn't have anywhere near the flexibility required to have the internet function in the way that it does. For that, we need Layer 4, and that's what I want to cover in this part of the lesson series. So what is Layer 4 and how does it function? Let's take a look. So far, this is what we have network model-wise. We've discussed the physical layer, which is Layer 1 of the OSI model. This relates to how raw bitstream data is transmitted to or received from physical shared media. We've talked about Layer 2, which adds identifiable devices, switches, and media access control, but Layer 2 ends with isolated Layer 2 networks. In the previous part of this lesson series, I introduced Layer 3, which adds IP addressing and routing so that packets can be routed from source to destination across multiple interconnected networks. Layer 4 builds on top of this. It adds two new protocols, TCP, which stands for Transmission Control Protocol, and UDP, which stands for User Datagram Protocol. Now, both of these run on top of IP, and both of them add a collection of features depending on which one of them is used. If you've heard the term TCP/IP, that means TCP running on top of IP. At a high level, you would pick TCP when you want reliability, error correction, and ordering of data. It's used for most of the important application layer protocols such as HTTP, HTTPS, SSH, and so on. Now, TCP is a connection-oriented protocol, which means that you need to set up a connection between two devices, and once set up, it creates a bidirectional channel of communications. UDP, on the other hand, is faster because it doesn't have the TCP overhead required for the reliable delivery of data. This means that it's less reliable. Now, there's a great joke about UDP. I would tell you about it, but you might not get it. Anyway, it's a good job my lessons are better than my jokes. In this lesson, I'm going to spend most of my time talking about TCP because it's used by more of the important protocols that you will use day to day on the internet. But just know that both TCP and UDP, they both run on top of IP and they're used in the same way. They use IP as transit. TCP just offers a more reliable connection-oriented architecture, whereas UDP is all about performance. So they're a simple trade-off. Now, for this lesson series, as I talked about, I'm going to be focusing on TCP because that's what's used for most of the important upper layer protocols. So let's take a look at exactly how TCP works. TCP introduces something called segments. Now, a segment is just another container for data like packets and frames before them. Segments are specific to TCP. Before we get started talking about the segments themselves, it's important to understand that segments are actually contained in, which is known as encapsulated within IP packets. So let's say that we have a stream of packets. You know by now that these are all isolated packets. They're just pieces of data which are routed independently from source to destination. They're all treated separately. Well, TCP segments are placed inside packets, and the packets carry the segments from their source to their destination. Segments don't have source or destination IP addresses because they use the IP packets for the transit from source to destination. This is all handled by Layer 3, in this case the Internet Protocol. TCP segments add additional capabilities to IP packets. Let's step through the structure of segments so that we can fully understand them, and I'm going to skip past a few attributes of segments just as I did with layer 3, because there are some parts which are less important or they're situational, so I won't be covering either the options or padding fields within a segment. The first fields which I want to cover are the source and destination ports. In addition to the source and destination IP addresses that IP packets provide, TCP segments add source and destination ports, and this gives the combined TCP IP protocol the ability to have multiple streams of conversations at the same time between two devices. When you open the AWS web interface, you're communicating from a port on your local machine to a port on the AWS servers, TCP port 443, which is HTTPS. Now, because of ports, you can have multiple streams of communication from your machine, one to AWS, one to Netflix, and one to this website where you're watching this video. At the other side, AWS can have multiple streams of communication to their servers. Each conversation is a unique combination of the source and destination IP, the source port, and the destination port. All of these four values together identifies a single conversation, a single communications channel. These two fields are what allow the internet to function in the flexible way that it does. It's why SSH and HTTPS can exist on the same EC2 instance, and why you can have multiple SSH connections open to the same EC2 instance if you wanted to, and I'll cover more about how this works as we move through this lesson. Now, next within the segment is sequence, and the sequence number is incremented with each segment that's sent, and it's unique. It can be used for error correction if things need to be retransmitted, and it can be used to ensure that when IP packets are received and the TCP segments are pulled out, they can be correctly ordered. So the sequence number is a way of uniquely identifying a particular segment within a particular connection so that both sides can make observations about it, and the way that these observations are done is using acknowledgements. The acknowledgement field is the way that one side can indicate that it's received up to and including a certain sequence number. Every segment which is transmitted needs to be acknowledged. Remember that TCP is a reliable protocol, and so if a device is transmitting segment 1, 2, 3 and 4 to another device, then the other device needs to acknowledge that it's received segment 1, 2, 3 and 4, and this is what the acknowledgement field is for. So sequence number and acknowledgement are used hand in hand. Next we have a field called flags and things. Now within a segment there is an actual flags component which is 9 bits, and this allows various controls over the TCP segments and the wider connection. Flags are used to close the connection or to synchronize sequence numbers, but there's also additional things like a data offset and some reserved space. So I've called this flags and things. It's essentially the flags plus a number of extra fields which I don't need to go into at this point in the lesson. Now next we've got the TCP window, and this is interesting. This defines the number of bytes that you indicate that you're willing to receive between acknowledgements. Once reached, the sender will pause until you acknowledge that amount of data, and this is how flow control is implemented. It lets the receiver control the rate at which the sender sends data. If you use a smaller window, it provides additional levels of control over how quickly you're sent data. Larger windows are more efficient because the header of a TCP segment takes up an amount of space, and the smaller the window, the more headers are involved. So this window setting is quite important if you're using TCP for practical reasons, but we don't need to go into too much detail in this lesson. Next we have checksum, which is used for error checking. It means that the TCP layer is able to detect errors and can arrange for retransmission of the data as required. And then lastly, we have the urgent pointer, and this is a cool feature. Imagine if you have a data transfer application where 99% of data is the data being transferred and 1% is control traffic, so communication between the client and the server coordinating the actual data transfer. Well, setting this field in a segment means that both sides can have separate processing so that control traffic always takes priority within the communication. So any protocols which are latency sensitive and transfer data, such as FTP and Telnet, can use this field. Now all of these fields together are known as the TCP header, and the capacity of a TCP segment which remains is logically enough used for data. So that's a segment. They're placed inside packets and transmitted by one network stack, specifically layer 4 of one network stack, and received by another network stack using the layer 4 protocol, in this case TCP. Okay, so this is the end of part 1 of this lesson. It was getting a little bit on the long side, and so I wanted to add a break. It's an opportunity just to take a rest or grab a coffee. Part 2 will be continuing immediately from the end of part 1, so go ahead, complete the video, and when you're ready, join me in part 2.